Think about this.
Mm.
A plane, right, powered just by sunlight, stays up indefinitely.
Yeah, the solar impulse. Professor Ghosh mentioned seeing it back in his 2021 course.
Exactly. From his renewable energy course at ICT Mumbai, it just blows your mind how that's even possible.
It really does. And that's what we're diving into today.
Welcome to the deep dive. We're digging into Lecture 12 of that course, GTT 2105, all about the foundational stuff behind solar PV devices.
Precisely. We covered solar thermal in lectures 10 and 11. Now it's all photovoltaics, the science, the history, the surprising connections.
Like how research in one area, maybe totally unrelated, suddenly clicks for something else. And LEDs too, right, towards the end.
Yep.
Okay, so let's kick things off. Where did this whole idea start? Light making electricity.
Well, it goes way back. Professor Ghosh pointed to Edmund Becquerel, 19th century.
Okay.
He basically noticed that light hitting certain metals could cause them to emit electrons, a really fundamental observation.
Just that simple. Light makes electrons move. Wow.
Yeah, showing light could have an electrical effect.
And Professor Ghosh mentioned the photocopy machine.
Mhm.
Not exactly the same tech, but the principle.
Kind of related, yeah. Selenium being light sensitive, light neutralizes charge, toner sticks. The core idea is light affecting charge.
Got it. So light can mess with electricity.
Yeah.
But then Einstein comes along.
Ah, yes, the photoelectric effect. And what's fascinating, what Einstein figured out was it's not just how bright the light is.
Right. It's something else.
It's the frequency of the light that matters. That's the key to knocking those electrons loose.
Frequency,
Yeah.
like the color of light.
Exactly. He introduced the work function. Think of it like a minimum energy level. A photon needs enough energy tied to its frequency to eject an electron.
So like a specific key to unlock the electron?
Precisely. And this tied into quantum mechanics, Planck's ideas, light acting like packets of energy, not just waves. That was the real aha moment.
Okay, so specific energy packets needed, not just any light. And someone proved this.
Robert Millikan, he experimentally confirmed Einstein's theory, that threshold frequency idea.
Right, so the science groundwork was there.
Yeah.
But getting from that to an actual solar cell, that seems like a big leap.
Huge leap. And this is where the story gets really interesting. It involves a bit of an accident.
Do tell.
Around 1940, Bell Labs, an electrochemist named Russell Ohl.
Okay, Bell Labs, famous place.
But he wasn't trying to make solar cells at all. His work was driven by World War II.
The war, how does that connect?
They needed better rectifiers, devices that control current flow for detecting microwave radiation, for radar.
Radar technology. Crucial stuff back then.
Absolutely. Apparently, German planes were being shot down unexpectedly, suggesting better Allied radar. And existing detectors, like Edison's or Bose's, they were okay for radio waves, but microwaves, not so much.
So the military need for better microwave detection pushed the research, not sunshine power.
Exactly. That was the immediate driver.
And Ull thought silicon was the answer.
He thought highly purified silicon might work, so his whole focus was getting silicon incredibly pure.
Right.
Professor Ghosh mentioned it's a pity Ull didn't get a Nobel for this, you know, even though Walter Brattain, who did win for the transistor, credited Ull in his lecture for discovering the p-n junction in silicon.
Yeah, sometimes those foundational discoveries get overlooked for the big prize. So his purification method, zone refining, melting it.
Zone refining, yeah. You melt a section, impurities tend to travel with the melted part, leaving purer stuff behind. Silicon melts really hot, so it made sense.
And he did this in helium gas. Why helium?
Because helium's inert. It won't react. If you used air, the oxygen would form silicon dioxide. Nitrogen could form silicon nitride. Messes up the purity. Helium keeps it clean.
Smart. Okay, so he's purifying silicon for radar.
Mm.
Then what happened? The accident.
Well, he ended up with this piece of silicon from the crucible, but it wasn't uniform. It had different structures in it, like a uniform bottom, but a sort of pillar-like top and layers between.
Sounds like something didn't go quite right.
Or maybe it went perfectly right, just not how he expected. So being a good scientist, he started testing these different parts.
Okay.
He hooked up a battery, and he found something amazing. Connect it one way, current flows. Connect the other way. Nothing. Blocked.
Whoa. A one-way street for electricity.
Exactly. That was the discovery of the p-n junction in silicon. Right there. By accident.
Just stumbled upon it. And the P and N, that came from the battery terminals.
Yeah.
Positive and negative.
Initially, yeah.
Mm-hmm.
P for where the positive terminal connected and current flowed. N for the negative side. It wasn't based on some theory of P-type or N-type material yet.
But they figured out why later. That it was about the silicon itself.
Right. They realized tiny impurities are causing it. Some impurities, like phosphorus, have extra electrons that made it N-type, negative. Others, like boron, needed an electron, creating holes that made it P-type, positive.
So a tiny bit of the right stuff changes everything. Amazing. And where these P and N types meet the junction, there's this depletion layer.
Yeah, what happens is right at the junction, the free electrons from the N side jump over to fill the holes in the P side.
Okay, they combine.
They recombine, neutralize each other. So right there at the boundary, you suddenly have no free electrons, no free holes, just fixed ions left behind.
So no charge carriers.
Exactly. It creates this little insulating zone, an electrical field barrier. Like a hill the charges can't easily climb.
Okay.
Stops the current flow normally.
Okay, got it. An insulating barrier. So how do you get current through it, like in a diode?
You apply a voltage, a forward bias. If it's strong enough, about 0.7 volts for silicon, it kind of pushes the charges over that hill, shrinks the depletion layer, and lets current flow.
And the opposite, reverse bias.
That just makes the hill bigger, widens the depletion layer, and blocks current even more effectively. That's your basic diode function, one-way flow.
Okay, but wait, there's another accidental discovery here, right? The solar part.
Yes, this is the kicker. Ol has this PN junction silicon sample on his desk. He's experimenting and notices the current reading changes.
How so?
It was higher when his desk lamp was shining on the silicon. He turns the lamp off, current drops, turns it on, it goes up again.
No way. The light itself was generating current.
Directly generating current in the silicon PN junction. That was the accidental discovery of the photovoltaic effect in silicon.
Just like Becquerel saw, but in this specific purified junction silicon.
Exactly. And Professor Ghosh pointed out Ol's patent even described this generating an electromotive force of voltage just from light hitting it. No external battery needed.
Incredible. From radar research to the foundation of solar cells, the path is just wow.
Isn't it? And it then took Bell Labs about another 14 years, building on Ol's work, to make the first practical silicon solar cell. That was 1954.
14 years. So Old discovered the effect around 1940, practical cell in 54, and the efficiency.
About 6% initially, which sounds low now, maybe.
Well, compared to today.
Right. Professor Ghosh mentioned maybe 15% as a realistic max for standard silicon in 2019, though commercial panels now are pushing 22, 23%. But back then, they even called it a solar battery?
Yeah, 6% might seem small, but that invention, it basically enabled the space program, didn't it?
Absolutely critical. Powering satellites, Sputnik, all that early space exploration. Suddenly, you had power in space.
Transformative. So that period, 40 to 54, that was the real crunch time for figuring out how to make it work reliably.
Definitely. Going from Ol's weird little silicon chunk to making large, uniform PN junctions consistently, that was a huge materials science challenge.
So why silicon? Why did that become the material? Must have been other options.
Silicon had some big advantages. First, it's everywhere. Second most abundant element in the crust after oxygen.
Okay. Cheap and plentiful.
And it naturally grows a thin layer of silicon dioxide glass, basically when it hits air. That layer happens to have just the right optical properties, its refractive index, to act as an anti-reflection coating, helps get more light into the silicon.
Oh, neat. A built-in feature.
Yeah. Plus, it's stable. It holds up well at the temperatures solar panels normally operate at, under 120 Celsius or so.
Abundant, self-coating, stable. Makes sense.
Yeah.
But how do they make the P and N layers deliberately for these cells? Ol's was accidental.
That involved more innovation. Professor Ghosh highlighted C.S. Fuller, also at Bell Labs. He figured out how to diffuse boron atoms into the silicon surface.
Diffusion, like soaking it in.
Sort of, yeah, at high temperatures. This created a very thin, very uniform key-type layer on top of the N-type silicon base.
And why thin?
Crucial. Thin meant it was almost transparent. Most sunlight could pass right through it to reach the depletion junction where the action happens. And being low resistivity meant less energy lost as heat inside the cell itself.
Let the light through, don't lose power.
Got it.
What about getting the electricity out? Connecting wires?
Another clever bit, they found they could directly electroplate metal contacts onto that smooth, boron-diffused layer. Made a really good low-resistance connection, an ohmic contact.
Easier than other methods.
Much easier. Some other ways of adding impurities roughened the surface, which meant you might need to, sandblast it to make contact, potentially damaging the thin layer.
Oh, okay.
And incredibly, Professor Ghosh noted that boron diffusion method. It's so stable and effective, we haven't found a significantly better way in, 70 years for that P-type layer.
70 years. That's amazing durability. And they added another anti-reflection layer, too.
Yeah, often a thin coating of polystyrene on top of the silicon dioxide. Just another layer to trap more light, reduce reflections even further.
Layer upon layer of optimization. And these layers are super thin.
Incredibly thin. Around 2.5 microns, Professor Ghosh said. That's comparable to the wavelength of light itself. And later, for some applications, especially space, they actually put the N-type layer on top to better handle radiation damage over time.
Okay, so we have this optimized sandwich. P-type, N-type, depletion layer, coatings. How does sunlight actually make the current flow in this finished cell?
So sunlight photons hit the silicon, especially in or near that depletion layer. If they have enough energy, they knock an electron loose, creating an electron and a hole, the spot where the electron was.
Electron hole pair, right?
Exactly. And that built-in electric field in the depletion layer immediately separates them. Electrons get pushed to the N side, holes get pushed to the P side.
Okay, separation is key.
It is. Then, if you connect an external wire or circuit between the N side and the P side, those electrons want to get back to the hole, so they flow through your circuit.
Creating current.
Creating current. And the separation creates the voltage.
So one tiny cell makes a little voltage. How do we get rooftop power levels?
You connect them together to get more voltage. You wire cells in series, positive one to negative of the next, and so on.
Like batteries in a flashlight.
Exactly. So a typical 12-volt panel might have, say, 36 cells in series. Each makes maybe half a volt, but together they produce maybe 17-volt open circuit, enough to charge a 12-volt battery nicely.
Okay, series for voltage. What about more current, more power?
For more current, you connect multiple panels or strings of cells in parallel. All the positives together, all the negatives together. That adds up the current capacity.
Series for volts, parallel for amps.
Got it.
Good. And you mentioned the voltage drops when it's actually working.
Yeah, under load, like charging a battery, the operating voltage will be lower than that maximum open circuit voltage.
And you need diodes to stop backflow.
Right, you don't want your battery draining back through the panel at night. So diodes, often Zener diodes, are used as blocking devices.
Makes sense. And panel angle matters too, right? We touched on that before.
Definitely. Optimal tilt angle depends on your latitude, aiming to catch the most sun year-round. Lecture 11 covered that.
Is tracking the sun worth it?
It gives the most energy, but it's complex and costly. Fixed tilt, maybe adjusted seasonally, is usually the practical compromise.
Okay, so sunlight intensity, angle.
Mm-hmm.
What else affects output? Temperature.
Temperature is a big one and kind of counterintuitive. As panels get hotter, their voltage actually drops.
Really? Hotter is worse.
For voltage, yes. And since power is voltage times current, lower voltage means lower power output. So super hot deserts aren't automatically the best places for efficiency, even with tons of sun.
Huh. Didn't expect that. What about those terms, open circuit voltage and short circuit current?
Right. Open circuit voltage, BOC, is the max voltage the panel makes with nothing connected, no current flowing. Short circuit current, ISCEC, is the max current it makes when you basically short the terminals, almost zero resistance.
Extremes, basically.
Exactly. The sweet spot where you get the most power is somewhere in between on the current voltage curve. That's the maximum power point.
And that's where MPPTs come in?
Maximum power point trackers, yep. They electronically adjust the load on the panel constantly to make sure it's operating right at that peak power point, squeezing out every available watt.
Clever tech. Now, Professor Ghosh mentioned some of their own work innovations beyond the standard stuff.
Yeah, they were looking at managing that heat problem. One idea was using phase change materials, like special waxes, on the back of the panels.
Waxes, how does that help?
These materials absorb a lot of heat when they melt without getting much hotter themselves, so it helps keep the panel cooler. They even added metal turnings to the wax to help pull the heat from the panel into the wax faster.
Better thermal conductivity? Did it work?
The potential was pretty significant. Maybe a 40% power boost was mentioned in the lecture figures.
Wow. And they also combined PV with desalination.
Yes, really interesting integration. Using the waste heat from the PV panels to preheat the salt water going into a reverse osmosis desalination unit.
So using the heat that usually hurts efficiency to help something else.
Exactly. And it helped a lot. They saw like a 75% increase in purified water production and about a 43% increase in the system's electrical output, too.
Broader trend is definitely towards finding ways to utilize PV for both electricity and useful heat generation in these kinds of integrated systems.
And parallel to these technical improvements, the cost of solar technology has just plummeted in recent years, hasn't it? That's been huge for adoption.
Oh, absolutely crucial. While the initial invention was back in the mid-20th century, it's the dramatic cost reductions we've seen, especially in the last couple of decades, that have truly made solar PV a practical and widespread energy solution.
How dramatic are we talking?
Well, think about it. Costs were maybe around $70, even $80 per watt back in the 1950s or 60s.
Wow.
Recently, that number has dropped to just a few dollars per watt installed. And there was a remarkable 30% decrease occurring just between 2014 and 2019 alone.
What drove that massive cost reduction?
It's largely down to economies of scale mass production and continuous advancements in manufacturing technology. For example, learning how to produce much thinner silicon wafers without sacrificing quality saves a lot on material costs.
Makes sense. So, with these lower costs, what are the typical efficiencies of commercial solar panels we can actually buy today? We started at 6%.
Right. Nowadays, standard commercial silicon solar panels generally have efficiencies in the range of about 15% to 20%.
Okay, quite a bit better.
Yeah, and some higher performance panels you can get are pushing maybe 23% or even a bit higher.
Is there a theoretical limit for silicon?
There is. The theoretical maximum efficiency for a single-junction silicon solar cell just using silicon is calculated to be around 29%.
So we're getting closer, but still room to improve even with silicon.
We are. Now, to go beyond that 29% limit, researchers are developing multi-junction solar cells.
Multi-junction, what's that?
Think of them like sandwiches made of different semiconductor materials stacked on top of each other. Each layer is specifically designed to absorb a different part, a different color or wavelength range of the solar spectrum more efficiently than silicon alone could.
So capturing more of the available light energy.
Exactly. By layering materials with different band gaps, you can convert more of the total sunlight energy into electricity. These multi-junction cells can reach much higher efficiencies, well over 40% in some lab cases.
Wow. Why aren't all panels multi-junction then?
Mostly cost and complexity. They're significantly more expensive to manufacture. So they're primarily used in specialized applications where high efficiency is absolutely critical and cost is less of a constraint like powering satellites in space.
Okay. Trade-offs.
Always trade-offs. And it's also worth remembering that there's often a trade-off between achieving maximum efficiency and ensuring long-term stability and durability. Silicon, while maybe not the absolute efficiency champion, is remarkably stable and durable. It lasts a long time out in the elements.
Right, which is crucial for a decades-long investment like a solar panel. Despite all these impressive advancements, though, there are still challenges that need to be addressed for solar PV, right? It's not perfect yet.
Oh, absolutely. It's an ongoing process. Ensuring long-term durability and accurately predicting the lifespan of panels under various real-world conditions are still critical areas of study.
What about practical issues like maintenance?
A really significant issue, especially for large-scale solar farms, is the loss of power due to dust accumulation on the panels.
Dust. How much does that affect things?
It can be surprisingly high. Losses of up to 40% have been reported in some dusty environments if the panels aren't cleaned regularly.
40%, that's huge.
It is. And cleaning these massive installations, often in remote, water-scarce areas, presents a major logistical and economic challenge.
So what's the solution? Robots. Special coatings.
Both are being explored. There's ongoing research into developing effective, durable, and low-cost dust-repellent coatings. Automated cleaning systems are also being developed.
Any other operational challenges?
Well, things like bird droppings can also be a nuisance, causing localized shading in hotspots. And beyond the panels themselves, the cost-effectiveness and optimization of all the auxiliary components, the mounting structures, the reflectors if used, the tracking systems that follow the sun, those MPPTs we talked about, they all play a role in the overall system performance and economics.
Lots to consider beyond just the cell itself. Okay, so we've covered the fascinating journey of solar PV pretty thoroughly. Now, towards the end of Lecture 12, the discussion also touches upon a related technology, the light-emitting diode, or LED. How does that fit into this overall picture?
It fits very neatly, actually. In essence, LEDs are like the reverse of photovoltaic cells.
Reverse? How so?
While PV cells take light and convert it into electricity.
LEDs take electricity and convert it into light.
Exactly. The basic principle involves applying a forward voltage across a PN junction, just like we discussed for getting current flow in a diode.
Okay.
This forward bias pushes electrons from the N side and holes from the P side towards the depletion layer. When they meet and recombine across that energy barrier,
They release energy.
they release energy, yes. In certain semiconductor materials, a significant portion of this energy is released directly as photons, as light. That process is called electroluminescence.
So it's the same fundamental semiconductor physics, the p-n junction recombination that we've been discussing for solar cells, just, well, running in reverse.
Precisely. The energy released during recombination can manifest as heat, which is what happens in a regular diode mostly, or it can manifest as light. The efficiency of an LED in converting electricity to light is often quantified by its quantum yield.
Quantum yield.
Yeah, basically it's the fraction of electron-hole recombinations that actually result in the emission of a photon of light, rather than just generating heat. You want a high quantum yield for an efficient LED.
Makes sense. And LEDs typically operate at fairly low voltages.
Yes, usually within a voltage range of around 2 volts, depending on the color of the light being emitted.
And the impact of LEDs on the world of lighting, I mean, it's been nothing short of revolutionary, hasn't it?
Absolutely transformative. If you look back at the history of lighting technologies, you had incandescent bulbs, which are basically just hot filaments.
Very inefficient. Lots of heat.
Terribly inefficient, yeah.
Mm.
Then fluorescent tubes, sodium vapor lamps for streetlights. The invention of the first practical red LED back in the 1970s marked a really significant turning point, even though it wasn't very bright initially.
Just red at first.
Primarily red. Then other colors followed. Over time, LEDs capable of emitting all colors of the visible spectrum were developed, including the ones now commonly used in traffic lights, for instance.
Right, but the big leap was in brightness and efficiency, especially more recently.
Exactly. The true revolution came with the dramatic improvements in both the brightness, luminous efficacy, and the energy efficiency of LEDs, which we measure in lumens per watt. This really took off starting in the late 1990s and early 2000s.
The lecture highlighted some truly impressive figures on that efficiency improvement, didn't it?
It really did. To give you an idea, around the year 2000, typical white LEDs were producing maybe 17 lumens for every watt of electricity consumed.
Okay.
By 2005, that figure had jumped to about 70 lumens per watt.
Wow, big jump.
Huge. In 2008, it reached 100 lumens per watt. By 2010, it was around 150. And by 2019, Philips reported achieving an astounding 200 lumens per watt in a commercial product.
Goodness, so that's, what, a 10-fold to 12-fold increase in efficiency in less than 2 decades.
Pretty much, yeah. This incredible ramp-up underscores the power of continuous research and development in material science and device engineering. LED lighting really stands as a prime example of how we can achieve substantial energy conservation without compromising on the quality or amount of light.
It really makes you wonder about the theoretical limits, though. How much more efficient can LEDs potentially become? Is there a ceiling?
There is a theoretical maximum. For monochromatic light of a single color, specifically green light, at a wavelength of 540 nanometers, where the human eye is most sensitive, the absolute maximum efficacy is calculated to be 683 lumens per watt.
Okay, so single color green is the theoretical peak. What about white light, which is what we mostly use for illumination?
White light is a combination of various wavelengths. Because of how our eyes perceive that mix and the physics involved, the theoretical maximum efficacy for white light is lower, estimated to be somewhere around 350 lumens per watt.
Ah, so even though 200 lumens watt is amazing, there's potentially still room to almost double the efficiency of white LEDs.
Potentially, yes. It suggests that there is still room for further improvement and innovation in LED technology. Ongoing research continues to push those boundaries, looking at new materials, better device structures, ways to get the light out more efficiently.
And just to clarify, the units we use to quantify light, candela, and lumen, can you quickly remind us what they measure?
Sure. Candela, CD, measures the luminous intensity, essentially how bright the light source appears in a specific direction. Lumen, on the other hand, measures the total luminous flux, the total amount of visible light emitted by the source in all directions. Efficacy, the lumens per watt, relates the total light output to the electrical power consumed.
Got it. And these units are key for those theoretical efficiency calculations.
Exactly. And beyond visible light, we're also seeing the development and application of UV LEDs, ultraviolet light emitters.
What are those used for?
Things like sterilization, curing resins and inks, water purification, certain types of sensing. It's opening up entirely new applications beyond just general illumination.
Fascinating. And we can't talk about LEDs without mentioning the blue LED, right? That was a huge breakthrough.
Oh, absolutely fundamental. The invention of the efficient blue LED by Japanese scientists Isamu Akasaki, Hiroshi Amano, and Shuji Nakamura at Nichi Corporation was the missing piece of the puzzle.
Why was blue so important?
Because once you have efficient red, green, and blue LEDs, you can combine their light to create high-quality white light. Or, more commonly now, you use a blue LED to excite phosphors that then emit yellow and red light, and the mix appears white. That blue LED development earned them the 2014 Nobel Prize in Physics, precisely because it enabled energy-efficient white lighting.
So, a truly pivotal invention for the LED revolution. It seems like both solar PV and LEDs, while doing opposite things, light to electricity, electricity to light, are fundamentally connected through this amazing world of semiconductor technology and PN junctions.
Precisely. There are two sides of the same coin, in many ways, based on manipulating electrons and holes in semiconductors. And LEDs, as we've seen, really stand out as a powerful, practical example of energy conservation in action.
The transformative impact of LED technology on lighting across, well, countless applications is just undeniable.
It really is. Everywhere, from homes and offices to streetlights, car headlights, displays. It's changed how we light our world.
So, as we bring this deep dive to a close, it's truly remarkable, isn't it, to trace this interconnected journey from those initial, almost obscure observations of the photoelectric effect,
Yeah, going way back.
all the way to the sophisticated solar photovoltaic devices powering homes and satellites, and the incredibly efficient LED lighting that we pretty much take for granted today. It's a compelling story, and it beautifully illustrates that interplay between sometimes accidental discovery and very focused, deliberate engineering.
Absolutely. And what's truly important for you, the listener, to take away is hopefully an appreciation for the fundamental science that underpins these transformative technologies.
Right.
And also an awareness of the continuous ongoing efforts to push the boundaries, improving efficiency, driving down costs, and overcoming the remaining practical challenges in both solar PV and LED development.
Yeah,
It's a field that's constantly moving.
definitely. And for those of you whose curiosity has been sparked and are eager to delve even deeper into the physics and the historical details, we highly recommend checking out the source, Lecture 12 of the ICT Mumbai course on renewable energy resources.
It offers a much more comprehensive exploration, more detail that we could cover here.
For sure. And get ready, because our next deep dive will continue our exploration of solar energy, picking up with Lecture 13 from the same course. So expect even more fascinating insights to come on the solar front.
Which leads us to a final thought, perhaps, for you to ponder. Considering the rapid advancements we've discussed today, and knowing the theoretical limits that still exist, especially for LEDs maybe, what future innovations do you envision for solar energy and for solid-state lighting? Where do you see the next big breakthroughs happening? And maybe more importantly, what kind of profound impact might these future developments have on shaping the future of our world and our energy landscape?